Welcome to Unit 1, Lesson 9, Working with Radicals, Part 2. In the first section of this lesson, we're going to look at how we can simplify radicals that are being added and subtracted with one another. Now, to do that, we're actually going to take each of our separate radicals that we see in the adding and subtracting statement and first try and break it down into a simpler radical form. And we're going to do that just the same way that we did in our previous lesson. So when I say a simpler radical form, I mean, well, just what we did in our last lesson, trying to take a number, for example, like 24, and break it up into two factors, for example, 4 and 6, where one of those, the number 4, can be square rooted. And so when we do that, the number 24, or root 24, can be written in a simpler radical form with the whole number 2 multiplied by a smaller radical of root 6. Now, there's other combinations that equal 24, like 3 times 8 and 2 times 12, but none of them actually lead to anything where a number or a factor within that could be square rooted. And even in some cases, if you have more than one option for breaking up a number, we're always trying to break it up in a way that will produce the smallest radical piece still attached to it. And so in this case, the way we can simplify this the most is to have just a root 6 attached to it in this case. I can do something similar with 54 as well. It breaks up into root 9 and root 3, or sorry, root 9 and root 6. So that would just be 3 root 6 when I simplify it. And then I'm going to add that with, well, root 150. Once again, that could break up into, well, 25 times 6 would equal 150. And 25 can square root into just the whole number 5. So what I'm noticing here is that each of these different overall things that I have, these different terms, have the same radical piece attached to them. They have the same square rooted piece attached to them. And my instructions tell me that we're able to add and subtract like radicals. So it turns out adding and subtracting radicals is very similar to adding and subtracting polynomial terms, where you can add and subtract ones that have the same radical piece attached, just the same way that with algebra, we can add and subtract things that have the same variable and same exponent attached. So to do that, think of this as if we were doing a statement like 2x minus 3x plus 5x. Well, our final answer would have an x attached to it, and we would really just need to add and subtract those coefficients. We're going to do the same thing here, except our final answer is going to have a root 6 attached to it. And we'll just add and subtract the coefficients that are in front of those. So we would take 2 and subtract 3 and get -1. Then we add 5 and we get 4. So 4 is our coefficient, and root 6 is sort of like a variable that's attached, but really it's just a smaller radical piece that's attached to it. Now notice in order to do that, we had to start by breaking these up into their simplest radical form. So let's see how we can do that in a different one here. So my first step, I'm going to do the same way. And if you want, you can pause the video here and try and break up numbers like root 48, root 8, root 27, and root 72. Break them up into a form that has the smallest square rooted piece attached to it as you possibly can. So, for example, 48 could be broken into 2 times 24. But then I'd maybe need to take that 24 and try and break that up into smaller pieces from there. So I try and find a simpler way to do this. Maybe I could do 4 times 12. Well, again, I could do that, and I could then square root the number 4. But then I'd still have a square root of 12 that I would need to break up even further. It can be broken up and made even smaller. So the idea is that I'm trying to make it so that I can quickly get to the smallest possible radical piece attached. So here's what I got for each of them. It's going to be 3 times, and I'll just put in brackets what root 48 is going to become. So root 48 could become 4 root 3 if we break 48 up into 16 times 3. Then it's subtract 1/2 times, well, root 8 could become 2 root 2, because 8 breaks up into 4 times 2. Then it's going to be plus 2 times, well, root 27 could break up into 3 root 3. because it's also 9 times 3. And then it's 4/3 multiplied by, well, root 72 can be changed to 6√2. And that's because the number 72 can be 36 times 2, and then we square root the 36. So now it almost looks like I'm going to have some like terms. It seems like I'm sort of on the right track here, but I need to make sure I've sort of expanded this out and gotten rid of any of the brackets involved. So this first one's just going to become 12√3, just multiplying those number coefficients together. With the next one, we've got a 2 here and a 2 here. They can be reduced down to 1s. So it's really just taking 1/2 and multiplying it by 2. So we really just get 1 of those. So it's like we're subtracting a single √2 here, subtracting just 1 of those. We don't need to write a 1 in front because just writing √2 means just 1 of those. And then this will be 6√3. And then in this last one here, I'll do a similar little step where I can divide 6 by 3 and leave a factor of 2, as long as I can divide 3 by 3 to leave a factor of 1. So this is really going to be subtract 8√2. So I take a step back and look at what I have. I have this term here that has a √3 attached, and this term here that also has a √3 attached. And separately, I have this one with a √2 and this one with a √2. So let's combine those like terms together. So 12 plus 6 is 18. So that's how many copies of √3 I have. And then -1 subtract 8 is -9. That's how many copies of √2 I have. That's the simplest way that I can write that radical expression, but we can clearly see that it has been simplified. I've taken something that had actually 4 terms in this case, and I was able to simplify it down to just 2 using some common radical pieces that I was able to find. Let's see some more complex examples of how we can multiply radical expressions. So for multiplying radicals, in general, we should always remember this little note that we want to expand first, and then we still may need to simplify from there. That's something that we generally say about any type of multiplication of different terms. So let's expand first. 2√2 multiplied by √10. So to do that, we multiply any of the coefficients together. So you can think of this, if you want, as sort of like 1√10. So if you just see a radical with nothing in front of it, just the same way that if you see a variable with nothing in front of it, you can pretend it's just got a 1 in front of it. So let's multiply the number parts. 2 times 1 just gives us 2. And then we separately multiply the radical parts underneath a radical sign. So 2 times 10 is 20. So we call this overall multiplication product 2√20. Like so. That's how we multiply those. And now let's multiply 2√2 times 3, or -3√14. So it would be -6 when we multiply the coefficient parts. And √2 times √14 is √28. But now √20 and √28, we want to try and simplify them as much as possible, because then possibly they could have some common radical piece to them that we could simplify further. So √20, it's going to be 2 times √20. Just rewrite that a little neater. 2 times √20, so it'll be 2 times, and then I'm going to rewrite √20 as 2√5. Then it's going to be subtract 6 times, and instead of √28, let's call it 2√7. So now in this case, I would have 4√5 subtract 12√7. Each of those two terms has a different radical piece attached, so there's no further simplifying I can do. in a similar way that I would have in my previous examples. So this is actually where I'm just going to leave it. That's as simple as we can make this. Sometimes, though, we might have a situation that looks more like multiplying binomials. And so in this sense, we don't mean binomials that have variables involved, but we do have two separate terms inside one bracket and two separate terms inside another bracket. So it really is like we're multiplying two binomials. Well, in order to do that, we follow all the same rules that we normally would. We multiply 2 root 3 by each piece in the second bracket, and then we multiply root 5 by each piece in the second bracket as well. And then we'll try and do some simplifying from there. So this would be 2 root 9, which you might already see is something we can do to simplify that in our next step, but I'll leave it as 2 root 9 for now. Then the next one would be negative 8 root 15. Then root 5 times root 3 is positive root 15. And root 5 times negative 4 root 5 is negative 4, and then the 5's underneath the square root sign multiplied together to give us root 25. So there's a little bit of simplifying I can do here. This is really going to be 2 times the whole number 3, because the square root of 9 is just 3. For these other two middle terms now, I have negative 8 root 15, and then I'm adding 1 copy of root 15. So I have negative 7 of those, negative 7 root 15. And then for my last term, it's negative 4 times, well, 5 really, because 25 square rooted is just 5. So now I actually just have two pieces that are regular old numbers, and I'll put those together or beside each other so that I can do a bit of subtraction of them in my last step. I have 6, and then I also have a minus 20. And so it's usually preferred to put those number parts first and then our radical portion after. So I'll put the minus 7 root 15 afterwards. So that means overall we have negative 14 minus 7 root 15. And that's the final, most simplified way that we can write that result. Now, there's some other things we need to keep in mind. When radicals are divided, it produces something that can essentially look like a fraction. But in order for a fractional radical expression to be fully simplified, we need to what's called rationalize the denominator. So square root of something like 6. So square root of 6, square root of 6 is very similar to the square root of 2 and the square root of 3 and many others that can't be perfectly square rooted. It actually produces a decimal expansion, or in other words, if you put it into a calculator, you'd see a big long string of decimals that seem very random and actually randomly go on infinitely. Numbers like that we call irrational numbers, or in other words, they're not rational. And we don't mean that they're crazy or they don't have logic or anything like that. What we mean by they're not rational is that there's no possible way they could ever be represented as a fraction. That's what rational means. A rational number is one that can be represented as a fraction. But these weird square root ones, like square root of 6 and square root of 2 for that matter, they can't be ever represented that way, and we call them irrational. And it's actually very tricky to have these irrational numbers in our denominators. It ends up causing lots of future problems later on in some more complex types of problems that we won't so much get into in this course, but will possibly come up in later courses. And so it becomes very important for us to not have any square roots of numbers like this, so irrational numbers, in our denominator. So we need to try and find a way to rewrite this overall fraction that we see without a square root of 6 in its denominator. So we do something called rationalizing the denominator. And here's the little trick. Remember that this is like a fraction, and I can always multiply a fraction by 1. But I'm not just going to multiply by any old 1. I'm going to multiply by a very clever version of 1. Remember, we can always write the number 1 as anything divided by itself, because anything divided by itself is equal to 1. So that thing that I just wrote there, root 6 over root 6, it looks very fancy, but it really is just equal to 1. It's just the number 1 in disguise. So I'm really just taking my fraction and multiplying it by 1. But look what happens when I multiply by this very fancy version of 1. Well, on top, it looks like I've made things more complicated. I end up with, well, I'll just have to call it 5 root 6. On the bottom, I can multiply the two things under the square root together, so I have root 36. Well, that's actually nice because at least on the bottom, even though I can't do anything with the top, at least on the bottom, I can square root that. And it's just 6. So again, it looks like I haven't made this any simpler at all. So you might say, well, you asked me to simplify, and it looks like I've made it more complicated. But it is simpler in the sense that now at least it has a denominator that is a rational number, not something that's got one of those square root values that produces an infinite random decimal expansion. We've got just a regular whole number in our denominator, and so it's much simpler than the original fraction we started with for that reason. Let's try another one. So here we have a similar situation going on where we have root 40 in our denominator. So we will eventually have to do some rationalizing of this denominator, it looks like. But you should always try and simplify things as much as possible first. So remember that we can always just divide the things that are underneath the radicals first. So I can simplify this to just 1 over root 8. So from there, now that I have 1 over root 8, let's take root 8 and make that a little bit simpler as well. So it's really like 1 over 2 root 2. Now I need to rationalize that denominator. So how can I do that? Well, I could multiply both the top and bottom by 2 root 2 if I wanted to, but really it's just the square root of 2 part that I need to deal with. So really, I'm just going to multiply both the top and bottom by the square root of 2. So what does that give me? Well, it gives me root 2 appearing on top, and then it's 2 times the square root of 4. Or in other words, I'll continue over here, it's the square root of 2 over 2 times another factor of 2, or it's really root 2 over 4. That's the simplest way that I can write that one. So always try and use the division rules that we reviewed in our previous lesson first. That's what we did to go from our original one to this first step that I wrote down. And then from there, I used further rules that we learned in our last lesson to make it even simpler. But now, from there, we had to use this step to rationalize the denominator. Let's keep going. Now these last couple, C and D, are very strange looking, where I not only have radicals appearing in my denominator, but there's also 2 pieces that have radicals in my denominator, and they're subtracted. So I'm actually going to make use of a special little fact here. I want you to recall the difference of squares rules that you've seen before. This idea that if I have something like a minus b, and I multiply it by a bracket that's sort of the opposite of that, a plus b, what that ends up multiplying out to is that difference of squares pattern, a squared minus b squared. So what does this mean? Well, it means if I have 2 different pieces that I'll call a and b for now, let's do it in green. If I have 2 different pieces that I'll call a and b, and they're being subtracted, if I multiply by a bracket that's almost identical, but instead adds those same 2 pieces, a and b, what happens is that I end up with a result that actually just squares the first number and subtracts it with a squared version of the second number. Now, that is going to be a very useful thing for me, because if I want these square root symbols, these radicals, to eventually become not radicals anymore, we need to find some way to square those values. So what we're going to do is essentially, and let's think of this a bit differently, I'm going to think of this as my A value, and this is my B value. And in that sense, this denominator is sort of acting like this bracket. And I want to eventually get to a stage where both the A and B value are squared versions of themselves. So what does that mean? It means I have to multiply by something like this. We call that second bracket that I would multiply by the conjugate of the first bracket. And I'm going to show you what I mean by that. So I'll get rid of some of this extra stuff here. Okay. So here's what I mean by multiplying by a conjugate. I'm going to multiply by a fraction, once again, that's really just going to be equal to 1. Here's what I'm going to do. I'm going to make the denominator of this fraction 2 root 6 plus root 3. So notice this is now essentially acting like that. It's acting like the opposite but similar piece that I'm multiplying by. And I can do that as long as I multiply by the same thing on top. So again, this process is called multiplying by a conjugate. And that word conjugate just means that there's some relationship between these two things. So specifically, what I mean is that these two denominators are conjugates of one another, meaning that they have the same two pieces, but they are opposite in terms of the operation involved. That's all we mean by them. And so when we multiply the denominator by its conjugate, we're going to be able to eventually get this squared or difference of squares pattern emerging. But in order to satisfy our basic math rules, we still have to make sure that we're using that same conjugate on top so that this overall fraction is really just equal to 1 that we're multiplying by. Let's see what happens as we start to expand this. Well, on top, it's going to start to look more complex. We're going to have 6 root 6 plus 3 root 3. But what about on the bottom? Well, now keep in mind that this is really like taking this in a bracket and multiplying it by this in a bracket. So we need to follow our binomial expansion rules. We would get 4 root 36. But then in difference of squares, if we go back and we review for a minute difference of squares, in a difference of squares, when we multiply two binomials like this, we end up with just the square of the first thing subtracted with the square of the second thing. So really, I don't need to write any middle terms or multiply out any middle terms. I can just square the first piece. So that's how I got 4 root 36, and square the second piece and subtract them. So I'm going to subtract root 9. So on top, I have the same thing, 6 root 6 plus 3 root 3. But now on the bottom, it's really 4 times the whole number 6, subtract 3, and I can keep simplifying. This would be 24 minus 3. I'm running out of room, so let's do it beside, because we have a little bit more we can do. This is all over 21. And now at this stage, we might think that we're totally done, but if we try and think back to the final examples that we did in our previous lesson, we also have to look for common factors that we could pull out on top and possibly divide or reduce with things on the bottom. So what I'm going to do is common factor out a 3 on top, and I'd be left with 2 root 6 plus root 3. And the reason why I did that is because that divides nicely with something that I have on the bottom as well. So I can divide the top by 3 and leave a 1, and divide the bottom by 3 and leave a 7. So in a slightly more simplified form, I would have just 2 root 6 plus root 3 all over 7. And that is the final, most simplified form of what I have. Let's try one more example of this conjugate idea. So now, this is the denominator that I'm trying to rationalize. Right now, those two pieces this time, though, are being added. So when I try and multiply this denominator by its conjugate, I need to just be a little more careful. So now the thing I'm going to multiply by has to have the same pieces involved, 2 root 3 and 3 root 7, but to be a conjugate, it has to have the opposite sign. So I'm going to multiply this by, I'm going to include a subtraction symbol in between now. So that again, these are conjugates or opposites of one another. And I can do that as long as the top is the same, 3 root 7. So that means I'm going to have some complex multiplying I'm going to have to do on top of all of this. But it, in the end, will produce something that does not have any radicals on the bottom. That's the goal. So let's start to multiply now. On top, we get 4 root 21 minus 6 root 49 minus 2 root 9 plus 3 root 21. That's what's happening on top. What we should start to notice on the bottom, though, is that we should be getting things that can be reduced into just regular whole numbers. So remember that those two denominators now are going to multiply out into essentially a difference of squares. So 2 root 3 times 2 root 3 is 4 root 9. There aren't going to be any middle terms, so it's just going to be subtracted with 3 root 7 times 3 root 7 is 9 root 49. Well, the things that have the root 21 attached, I can combine together. So there's 7 of those. 7 root 21 minus 6 times 7, because that's what root 49 is, and minus 2 times 3, because that's what root 9 is. On the bottom, it's going to be 4 times 3 and 9 times 7 when I do some square rooting there. So now I have 7 root 21 minus, when I put all those numbers together, it's minus 42 and then minus 6, so minus 48. On the bottom, 4 times 3 is 12. Then I subtract 9 times 7, so I'm subtracting 63. I would get negative 51. And then the only additional thing we should do to fully simplify this just a little bit further is recognize that we should never have a negative in our denominator either. So we definitely don't want there to be any radicals in our denominator, but we also don't want there to be a negative in our denominator. So if our denominator is negative, we can just instead make it positive and make our numerator negative in its place. So when I do that, I just have to be careful that I make the entire numerator negative, which means I need to flip the sign of every term in the numerator. So I get negative 7 root 21 plus 48 all over positive 51. And that is the fully simplified version of that original statement. So again, it all came back to that idea of multiplying by a conjugate. And that conjugate was specially chosen so that it includes the same terms that I have in my original denominator, but with the opposite sign. And when that occurs, we'll end up with this multiplication that really leads to essentially like a difference of squares product. those squared things that are part of that difference of squares then can be easily square rooted into nice whole numbers, and we've rationalized our denominator, and then we just simplify from there.